All right, here we go. So more integration. So we're going to look at four rational functions right now and see that they're all going to be done in a very different way. Right. So here we go. So we want to integrate this. So I certainly don't recognize a function whose derivative is that. So what are my options? Right. Well, let's see. Integration by parts. It doesn't look like that's going to work. I can't factor the bottom using rational numbers. So linear partial fractions is not going to work. So, oh, maybe what was that thing with quadratics? I can complete the square, right, on the denominator in this case. So let me go ahead and do that. So x squared plus 6x, right, kind of keep that separate from the 10. And what I want to do now is I want to add that magic number, which is always going to be half of b squared. So half of 6 is 3, squared is 9. Now, I kind of got lucky here because if there would have been a coefficient on the squared term, I would have had to have taken it out of the squared term and the x term. But I didn't because it's 1, so I'm good to go. And so I'm going to add 9 to the denominator, but you can't just do that. That changes the problem. So at the same time, I'm going to subtract 9. So I basically added 0 to this expression, so you'd all agree that that's something you can do. Right? Now what's cool is what we just did is we just created a perfect square trinomial, hence the name completing the square. This can get factored as x plus 3 quantity squared. 10 minus 9, well, howdy doody time. That's a big deal that it's 1. It really needed to be 1, or we really wanted it to be 1, right? So, all right, so what does this do? Well, let's come over here. Let me first pull the 3 out because it doesn't need to be there. Integral 1 over, and then I'm going to do x plus 3 squared plus 1. So you're like, how is that any better? Well, because now I recognize this. I see the structure. Right? Do I know a function whose derivative is 1 over stuff squared plus 1? Hopefully you are saying, oh, I certainly do. It's arctangent of stuff, right? So it's going to be, here's my 3, my constant, times the arctangent of stuff. And then really, it's since stuff is linear, right? It's the only reason why we can do this. It's going to be times 1 over the derivative of stuff. Now, it's 1x plus 3, right? So the derivative of that is 1. So then I end up getting plus c. And so my final answer is going to be 3. And maybe I'll just get fancy and write arctan x that way. Arctan of x plus 3 plus c. And that's it. All right. So pretty quickly. So we complete the square so that we can recognize that inverse trig derivative. If you were to take the derivative of this and just think about it, right, this would be 3 times the derivative of arctan of stuff. It's going to be 1 over stuff squared plus 1 times the derivative of stuff. You, in fact, would get this. And if you multiply this out, you would get that. All right, so that's kind of a big deal. Remember, there's 2 little kind of things that we're doing here. Right here, I did like a linear U. So if you want, maybe for node flow, just to show it, right, what did I do here? I said, hey, let's let U equal x plus 3. So du then is going to be 1 dx. So now this integral can be written as 3 integral of, let's see, all of this is du. That's going to be, I'll just write 1 over, and it'll be the du over there. I could write du over, but I want to write it this way. And then this is going to be u squared plus 1. Do you know a function whose derivative is 1 over u squared plus 1? And again, you should say yes. We just did it. It's arctangent of u, right? So 3 arctan of u, and then plus c. And then if we go ahead and we do this, back substitute, right? You picked u is x plus 3. So you're going to get the same exact thing that we got right here, all right? But because we had a linear u, we can kind of think of it as stuff and do in your head and multiply by 1 over the derivative of stuff. And the reason for that is because if this would have been like 3x plus 3, then you would have multiplied by 1 over 3, right? Because the derivative would have been 3 here, and then you'd have to move it over and do 1/3 du equals dx. All right, moving on. Next problem. So we take a look at this and you're like, all right, am I going to complete the square on the bottom there? Because it's basically the same expression. And the answer is no, you don't want to, because what's going to happen here, right? Because you'd end up getting what? X plus 3 over that stuff squared plus 1, right? That's not going to help you. What's going to happen here, what you want to happen here is just a regular u sub, right? So if I let u equal x squared plus 6x plus 10, du would be 2x plus 6 all of that dx. Now that looks a little weird, but if I multiply both sides by a half here, I'm going to get x plus 3 dx, and now you can see, oh no, that's not weird. That's this right here, right? A u sub in the prior problem would not have worked because this is what your du would have been, and That's what I like to call too much function, right? You only had a 1 in the numerator in the prior problem. So all of this in this little box here is 1/2 du, right? All of this here is just going to be u. You let u equal that. So now if I rewrite this, right, I'm going to pull the half out. I have the integral of du over u. Or if you want, 1 over u du. It's the same thing. You don't have to show both. Whatever floats your boat, right? So like, okay, how do I do this? Do I know a function whose derivative is 1 over u? Hopefully you're saying absolutely. It's going to be ln absolute value. Maybe the pun was intended there. Ln absolute value of u plus c. That's it. That's a function whose derivative is that. And so now you know what u is because you picked it. So it's going to be ln absolute value of u is x squared plus 6x plus 10, and then plus c, and then call it a day. And that's going to be your answer. All right, so it's kind of a neat question, right? Because you look at this and you're like, all right, that was 3 over, not 1 over, 3 over, right? That quadratic, and a u sub here ain't going to get you to the promised land. It doesn't work. So you had to go ahead and complete the square on the denominator so that you can recognize this. Whereas in this question, you don't want to complete the square on the denominator. You actually try u sub. And really that should kind of be the method in which you exhaust your possibilities. So you should really try a u sub before you do something like completing a square in a denominator, right? So u sub is one of the earlier techniques you want to try. All right, let's take a look at 11. So you're like, what's the deal there? Got another quadratic, but now this is a little different in that the degree of the numerator is higher than the degree of the denominator, and that really should tell you what to do. So hopefully, maybe pause the video and think about it. What should I do here? All right. If you're back, u sub's not going to work. If you let u equal the numerator, you're going to get a du of 2x plus 6, right? And you're like, all right, that's some multiple of x plus 3, isn't it? But this isn't x plus 3, right? This is 1 over x plus 3, right? This x plus 3 is in the denominator. So letting u equal the numerator is not the way to go. So the actual way to go, when the top is a higher degree, one of your little tools in your bag of integration tools is to long divide, right? And you could synthetically divide here, but I'm going to show the long division. So if we go ahead and there's no fillers, right? I didn't miss any x's or anything like that. Go ahead and long divide. So remember how we do this. We look here, we look here, we look nowhere else. We say, hey, what do I need to multiply u by in order to get u? And the answer is x. And now you distribute. X squared plus 3x. Then you go ahead and you subtract, right? Subtract, subtract. So this is 0x squared. That's a clue I'm doing it right. 6x minus 3x, that's 3x. 2 terms, 1 term. So I bring down the 8 and I play the game all over again. I look here, now I look here. What do I need to multiply u by in order to get u? The answer is 3. And then I'm going to get 3x plus 9 when I distribute, right? Go ahead, subtract, right? So I have to subtract this whole thing. That basically means change all the signs. So you're going to get 0x, looks like I'm doing it right, and then 8 minus 9, that's -1. Circle it. That is your remainder, right? So this is your remainder. This is your quotient. This thing that you divided by is your divisor. So basically, right, maybe like a little review, if you had like, I don't know, 11 over 2, and you wanted to do that, you'd be like, all right, 2 goes into 11, let's see. 5 times 2 is 10, right? Subtract, get a remainder of 1, circle it. So what's my answer, right? It's 5 with a remainder of 1. So it's 5.5. So it's 5 plus 1 over 2. It's quotient plus remainder over divisor. That's the same thing that holds true here. So this fraction can be written as quotient x plus 3 plus remainder over divisor. Okay? So these two expressions are equal. And now this is easy. This integral of some integrals, you can integrate this. Integral of x, 1/2 x squared. Integral of 3, 3x. This one, not as easy, but you should start to be getting more comfortable with this, right? Do you know a function whose derivative is 1 over linear stuff? And hopefully you're saying, yeah, ln absolute value of linear stuff times 1 over the derivative of stuff. Now, again, stuff is 1x plus 3, so the derivative of that would be 1 over 1. I'm just putting that in there in case this is something other than a 1x, right? So cleaned up a little bit, it's 1/2 x squared plus 3x minus ln absolute value of x plus 3 plus c. Right? And if you're not following this from here to here, you can do a u sub here. Let u equal x plus 3, do it to the side, and you will get something in the form du over u, and you'll end up getting this, okay? So that's long division, okay? Let's do one more. Take a look at this guy. All right, so what do we do with this guy? Well, I can try completing the square in the denominator, but I'm not going to get something that I like. I'm going to get like x squared, x plus 3 quantity squared minus 1 or something to that effect, right? When I subtract 9 from 8, I get a minus 1, not a plus 1. So it's not going to be recognizable. So, all right, so what the heck do? I can't only divide the top is degree 0. That's degree 2. What are my options? Well, then, does a normal u sub work, right? Probably should have tried that first. Well, if u equals x squared plus 6x plus 8, du is 2x plus 6. There's no x up here. Too much function, that's bad. So long story short, yet another option to you is to do what we call linear partial fraction decomposition, right? Big fancy word. It basically means, hey, let's factor the bottom. So let me kind of come to the side and get a step out of the integral problem for a second and go ahead and factor this bottom. All right, so this bottom is factorable, x plus 2, x plus 4, right? If I multiply this out, I would certainly get that. So now what does that mean? That means this can get decomposed. Each linear factor, right, gets a partial fraction with that as its denominator. And it's always 1 degree less in the numerator. So if this is a polynomial of degree 1, a general polynomial of degree 0, well, that's just a constant. So we'll say capital A represents that constant. Plus the other linear factor gets 1 as well. And it'd be a different constant potentially up there. So I would just do capital B, right? So when you do this partial fraction decomposition, every non-repeated linear factor in the denominator is going to get a partial fraction. And if it's linear, it'll always be some constant over that linear factor. All right, it gets a little bit more complicated when you have repeated linear factors and quadratic factors, but not too much more complicated. Good news is you don't even have to know that. So now what the heck do? I got to figure out what A and B are, right? It's actually pretty easy. So is there a magical term that you could think of to multiply this equation by so that all of these denominators cancel? And hopefully saying, well, yeah, that magical term will always be right here, right? So if I multiplied this side by x plus 2 times x plus 4, and then multiplied this by x plus 2, x plus 4, and then multiplied this by x plus 2, x plus 4, take a look at what happens, right? So here, these gonzo, so you just get 3 over here, all right? Here, the x plus 2's gonzo. Here, the x plus 4's gonzo. So what are you left with? You're left with 3 equals a times x plus 4 plus b times x plus 2. Now, here's the kicker of this. This is an equation that is true for all values of x. So let's pick a convenient value of x to maybe make one of these variables go away. So what do you mean? Well, like, watch what happens if I let x equal -4, right? And I didn't just pull that out of nowhere. That's what makes this factor 0, right? So I'm going to get 3 equals, well, -4 plus 4 is 0, right? So I guess I could write this for node flow. And then this would be -4 plus 2, right? So 0 times a, well, that's great. That's just 0. The a goes away. I end up getting -2, right? B here. So I can solve that for b. Divide both sides by -2, and I'm going to get -3/2 equals b. So that's great. I got that right there. So now what else could I pick? Well, I could also pick, if I wanted, another x value, because this is true for all x values. So what would, I can plug anything in, to be quite honest, but what would be a good value to plug in, right? Well, I would say -2 would be a good value to plug in, because watch what happens. 3 equals a times -2 plus 4 plus b times -2 plus 2, and you're like, oh, look at that. So now this is going to be 0 times b. That's going to wipe the b out. So I'm going to end up getting, let's see, -2 plus 4, that's 2a. I'm going to get 3/2 equals a, right? So that's great. So now I know what a and b are. So that means, right, this fraction is equal to the sum of these two fractions. So I can rewrite this integral problem as the integral of a, which is 3 over 2 over x plus 2, right, plus b, which was -3 over 2 over x plus 4, right? If I was to add these two fractions, get a common denominator, do the whole thing, or do fastest technique on demand, I would get that. So these are equivalent. And now, why is this good? Well, integral of the sum of the integrals, 3/2 just a constant that's going to get pulled out in this first integral. And then do you know a function whose derivative is 1 over x plus 2, right? 1 over stuff, 1 over linear stuff with a derivative of 1, by the way. Hopefully this is getting easy breezy, and you know that's ln absolute value of x plus 2. And then it's going to be basically the same thing over here, just a different constant and a different linear stuff. So a function whose derivative is this is going to be negative 3 halves ln absolute value of x plus 4. And then don't forget your plus c, call it a day. All right, so that was pretty easy. So we decompose this fraction, basically backwards added fractions, to express this as a sum of two smaller fractions that we were able to integrate. Okay, pretty cool stuff, let me tell you. All right, that's video 3. We only got one more left.